Okay, so metals, specifically metallic bonding, all right? So we've talked about covalent bonding, yes, and ionic bonding. All those have to do with stealing or sharing of electrons, right? Metals are all about free love when it comes to electrons, okay? They all just share their valence electrons, okay? When we talk about the periodic table, which
are you sure you said that right?
I said it in you know, a southern accent. America. What other languages do I speak?
No, just say it's a different language.
Portuguese,
Yeah.
Portuguese, Spanish, a little bit of German. I used to be good at German, then I learned Portuguese, and the German just went away out of my brain. Okay, so if we look at the periodic table.
Have you listened to the metal band that's a German metal band that sings in Spanish?
Yes.
It's pretty great.
Yeah. Okay. So in the middle here we have metals. Yes. Metals. Okay. Here in the middle we have metals. All right. On this side, remember on the left side of the periodic table, these really want to give away a valence electron or two, right? And on this side, all these really want to steal a valence electron or two, right?
It's like kids with Red Bull.
It's like kids with shit. In the middle, they don't really care about their valence electrons. It's just like, hey man, you can have a valence electron for a little bit as long as I get it back for a little bit and we'll just share. And it's like Ryan playing that game. You can win this one if I can win that one, and we'll just work together, right?
Cooperation is for the weak.
Cooperation is for the weak. So you can get bonds between atoms of metal that are truly enormous. You can get millions, billions, trillions of metal atoms to essentially become one thing. Billions and billions of atoms. Yes, as Carl Sagan would say. Okay? So if we look at iron here, all right? Iron atoms like to be around other iron atoms, and they just share, right? Iron will react with other stuff, but they don't care really who they're with. They just like to share their electrons, okay? Cobalt, nickel, copper, zinc, all of these that are pink in the middle are totally cool sharing electrons with one another, okay? These are metallic bonds, and they look, again, like this. We have these free valence electrons just moving in between atoms. This is why metals conduct electricity so well. Does that make sense? What is electricity? It's electrons moving, right? It's electrons moving. Well, because these atoms are so cool with just taking and receiving valence electrons whenever the heck they want to, this makes the conductivity of electricity super high in metals. Okay? So do we see how the atomic behavior, the molecular behavior of materials can affect the real world, like electric conductivity? Yes? Okay. So in this case, we have metals of all kinds, of all the same kind. Okay? So for instance, we use the example of a chunk of iron, right? Well, sometimes we can get pieces of metal that are not all one element, right? Sometimes we get what are called alloys, okay? Sometimes we get an alloy. What is an alloy? Can anyone describe to me what an alloy is? Okay, I need one person to raise their hand and then give me, Jack.
It's a combination of more than one metal.
Yes, it is a combination of more than one metal.
Steel an alloy?
Yes, steel is absolutely an alloy of iron with some carbon in it. Okay? And this is what it looks like. Right here. Okay? We have iron atoms with some carbon atoms thrown in. This makes the iron stronger. Okay? This is called an interstitial alloy. Interstitial alloy, okay? Let me demonstrate that with a better picture here. This is a pure metal. So let's just say that this is pure iron. Let's actually use let's use zircon. Zirconium. Yeah, that'll be fine. Okay? It's just one type of element, all uniform. An interstitial alloy is an alloy when you have the pure metal and then you combine it with something that has a significantly smaller atomic radius. So the atoms can literally fit in between the other atoms. So an interstitial alloy is when we have small atoms fitting in between larger atoms. This is an example of steel. Okay? This is an example of steel. Steel is iron with carbon in between. The carbon atoms sit in between the iron atoms, and that's the reason why steel is stronger than pure iron. Because the carbon atoms help to hold the iron atoms together. They provide extra structure. Does that make sense?
Does that ever happen where there's like an interstitial alloy that's just every dot?
You can get an interstitial alloy where you can get an atom in between each and every larger atom.
Does that make like real strong?
Yes, you have to cool it really, really slowly. If you cool it quickly, then what happens is that the atoms are kind of jumbled, and you can get weak points in the metal because the atoms are not equally spread. And really, you have to do a lot of, you guessed it, stoichiometry. Oh my gosh. If you want to make a really strong steel, you want to find the perfect stoichiometric ratio between iron and carbon. And then you melt them together and you let them cool really slow. And the carbon atoms will find the little tiny pockets in between the iron atoms, and you get a very strong steel. Repeat. Over the course of, I mean, anything in the order of minutes is extremely slowly for atoms. The speed at which atoms move is ridiculous, right? So if you cool it over a few minutes, you you don't flash cool it like in some cold water or cold oil. Yeah, okay? Now we can look at a substitutional alloy, all right? Let's use a different example. No, let's not actually. So if this is iron again, we've got the red iron. Looking at the periodic table, let me see here. I have too many tabs open. Looking at the periodic table.
How many of them are just periodic tables?
A few.
So why not use something?
If we were to look at a periodic table, goodbye. So this is a substitutional alloy. What do we notice about a substitutional alloy versus an interstitial alloy? It's not a smaller radius. How are the atomic sizes related in a substitutional alloy? Wilkes?
Maybe they're pretty similar.
They're very similar, right? The blue dot is similar in size to the red dot, okay? So if we are to look at our periodic table, here's iron. Where could we find a metal with a similar atomic radius? You're gonna have to go back in the library of your brain and you're gonna have to pull out the book that says atomic radius.
It would be close to iron.
It would be close to iron. Give me an example. Cobalt. Okay? Cobalt and iron are really good for making a substitutional alloy because they have very similar atomic radius. So let's look at the atomic radius of cobalt. If we look on the left side here, I know it's very, very small. Let me zoom in here. Cobalt has an atomic radius of 152 picometers. Okay? Iron has an atomic radius of 156. It's pretty close. Whereas iron has 156, carbon is 67. See how big the difference is there? With cobalt, we can replace a few of the places of iron atoms with cobalt atoms, and we can get a substitutional alloy. Yes, good sir, Reapy Stoll.
What is the atomic radius
of palladium? 169.
Are there any that have the atomic radius of just straight up 69?
Boron, nope, 87. What do we think here? Maybe sulfur? Nope. Chlorine? Close. Argon? Ooh, close. 71. Oh, bummer.
I assume it's a no, but are there any that have to be 420?
Are there any bigger that are 420?
Are there any atoms big enough to get it?
Lead, no. We don't know.
No, they're only like half.
222, yeah. Okay.
Man, what idiot atoms?
What idiots? I want them to be funny numbers, says Jack.
Yeah, pretty much.
Yes, like the Tesla Model S, currently priced at $69,420.
And there's the Model S, the Model 3.
Model S3XY. Right? No. It gets better. Cybertruck, C. ATV, A. Roadster, R. Semi, S. SE, S3XY, CARS, because everyone that works at Tesla is a child. All right. A very, very smart child, but still a child. Okay.
No longer the richest man in the world because Bitcoin went.
Okay. So, do we have any questions about interstitial versus substitutional alloys?
No.
Alloys are super, super helpful. We can make all sorts of cool alloys. Well, using the royal we. People like metallurgists and chemical engineers can make really cool alloys that are strong or light or really conductive or sometimes conductive, or they're good at insulating heat, or they're really good at conducting heat, just based on using the chemical properties of the different elemental metals. They're able to combine multiple elements to make an alloy with the characteristics that we want. They're essentially doing selective breeding.
Eugenics?
Not eugenics. No, let's not get into eugenics. They're essentially doing selective breeding like we do with dogs, but with metals. Like, hey, this dog has floppy ears and is really big. I would, or this one has floppy ears. I want a very large floppy-eared dog. Let's take a floppy ear medium size and a very big non-floppy ear, and we'll combine them together and see if we can get a floppy ear big dog. And
Let's just stop doing that. You're going to ruin half the step of chemistry. Let's just.
oh, I can ruin dogs all I want.
Let's go. Let's
You
see.
know what makes a pug alloy? You see,
A pug alloy, but it's spelled with 2 G's and a Z. Pugs, like the cheap what sunglasses brand. Pugs.
here's the thing, Mr. Crush. You could, but what if, hear me out, you didn't?
What if you didn't? Okay,
What if I offer you a Girl Scout cookie for peace?
for peace, I offer you peace. All right, I'm gonna end the video there. We're gonna continue talking about compound properties going forward. But we need to do the assignment about chemical engineering. Let's get into it. So like and subscribe or whatever I'm supposed to say.